In this video, we'll convert a basic relay control circuit into a PLC program. The example circuit is a basic 3-wire control scheme using a motor starter, as well as indication for the motor being on or off. The first step in this conversion will be to identify the necessary input and output devices that will be wired to our PLC. In the case of inputs, we'll need to wire the push buttons, both PB1 and PB2, as well as a normally open auxiliary contact from the motor starter to provide positive feedback about the motor's state. We will not need to wire the normally closed contact, as the logic of the normally open auxiliary contact can be inverted with our PLC's logic. Additionally, the normally closed contact from the motor starter's overload relay will be hardwired in the output circuit, not as an input to the PLC. As for output devices, we'll wire the motor starter coil, MS1, and the 2 pilot lights, PL1 and PL2. The next step is to generate a wiring diagram. This document will establish which terminals on the PLC our real-world field input and output devices will be connected to. In this example, we're using a 1769 L18ER-BB1B Allen Bradley Compact Logic processor with embedded inputs and outputs, as well as several add-on I/O modules. Looking at the embedded input terminals of the PLC, we can see the real-world field input devices connected to various terminals. PB1, PB2, and MS1's auxiliary contact are connected to terminals 0, 1, and 2, respectively. Note the text to the right of each terminal. Each is a unique tag that will be used to represent the real-world field device while programming in the Studio 5000 environment. Observe how the tag is broken down into 3 separate components. First, the device designation. Second, a brief description of the component's function. And third, the normal state of the real-world field input device. As you can see, wiring diagrams for the output terminals are done in a similar fashion to those of the inputs. Here we can see the embedded output terminals of our PLC. Connected to channels 0 and 1 are PL1 and PL2 respectively. In addition, we can see that we will be wiring our motor starter's coil to the 120 volt AC expansion I/O module in slot 4. Also observe that the overload relay's normally closed contact is physically wired in series with the motor starter's coil. With this step complete, we can now move on to the Studio 5000 environment. First, we'll begin by adding our unique user-generated tags. In order to add our user-generated tags, we'll need to navigate to the Parameters and Local Tags folder located within the main program and continuous task folders. Next, we'll click on the Edit Tags tab, which will allow us to begin entering our user-generated tags. The first tag we'll enter is the one for PB1. We'll start by adding the tag name used on the wiring diagram. Next, we'll select Input Parameter under the Usage column. This ensures that the data associated with our tag is only updated at the beginning of a program scan. Next, we'll select the data type necessary to store information associated with this tag. Because the tag is associated with a discrete input device, we'll select bool. Next, we'll establish a connection between our user-generated parameter tag and the controller-generated module base tag associated with the input terminal that our push button is wired to. This is done by clicking on the drop-down icon located in the connection column. From here, we'll navigate to local:1:I, data, 0. This is the controller-generated base tag associated with channel 0 on the embedded input. The same steps will be repeated for the other input tags. When making connections between controller base tags and user-generated tags, one can also type the controller-generated base tag into the connection field. Next, we'll add our output tags using the same steps used for input tags. The only difference will be selecting output parameter when entering the usage. With the user-generated parameter tags created, we can now begin programming by navigating to the main routine. The first run of our program will be used to create the logic necessary to produce the 3-wire control of the motor starter. To accomplish this, we'll need to use 3 examine-if-closed instructions, with 2 of those being arranged in parallel using a branch. We'll also utilize an OTE instruction in order to control the output connected to the motor starter. Once the instructions have been added to the run, we can begin assigning their respective user-generated parameter tags. A second run will be added to produce the logic associated with the red indicator light for when the motor starter is de-energized. In order to produce this logic, we'll use a single XIO instruction along with an OTE instruction to control the red light. Lastly, because the logical conditions for the motor starter coil and the green indicator light are the same, we'll add a branch to the first rung and add another OTE instruction in parallel with the one added earlier, and assign it to the tag associated with the green indicator light. To finish off our program, we'll add run comments. Run comments are added by right-clicking on each rung and selecting Edit Run Comment. Run comments should provide other users with a clear idea of the logic performed by each rung. Once run comments have been added, the program is now ready to be downloaded and tested.